Hi, my name is Tiffany, and today we're going to be doing a careful walkthrough balancing redox reactions in neutral, acidic, and basic conditions. Oxidation reduction, or redox reactions, involve the transfer of electrons from one chemical substance to another. Two things happen in a redox reaction. One reactant undergoes oxidation, losing electrons, while another is reduced, gaining electrons. Electrons are negatively charged, so gaining them lowers an atom's overall charge. Many common redox reactions take place in an aqueous solution, so we need to consider the pH of that solution. A neutral aqueous solution has a pH of 7. It is neither acidic or basic. Here we have a simple redox reaction between metal chromium and silver 1 cation. The first step in balancing a redox reaction in any condition is to balance all atoms besides the oxygen and hydrogen. But our neutral example already has this covered. Next, we need to determine the oxidation state of each element. These will add up to the same value on both sides once the equation is balanced. The oxidation state is the apparent charge of an atom. In the case of free ions, the oxidation state is the actual charge too. An element in its monatomic solid form will have an oxidation state of 0. This includes the solid chromium on the left, as well as the solid silver on the right. The silver 1 ion has an oxidation state of +1, and the chromium 2 ion has an oxidation state of +2. With that done, it's time to use the half reaction technique to break down the equation to its reduction reaction and its oxidation reaction. An increase in charge means a loss of electrons, which means chromium is undergoing oxidation, going from an oxidation state of 0 to +2. A decrease in charge indicates that an electron was gained. Silver is being reduced because its charge was reduced from +1 to 0. We can say that chromium is a reducing agent or reductant because it's giving its electrons over to silver. This makes silver the oxidizing agent or oxidant, as it accepts the electrons. Here is the oxidation reaction of chromium metal to chromium 2 ion. To balance this half reaction, we need to add the 2 lost electrons to the right side of the equation. This is the reduction reaction of the silver 1 ion to silver metal. To balance this half reaction, we need to add the gained electron to the left side of the equation. Before we can combine them, we need to ensure that the right side of the oxidation reaction and the left side of the reduction reaction have the same number of electrons. Find the least common multiple between the two quantities of electrons. The least common multiple of 1 and 2 is 2. So we multiply the oxidation reaction by 1 and the reduction reaction by 2 to reach the least common multiple. Finally, it's time to reunite our half reactions. Add the corresponding sides of each equation together, left with left and right with right. Then cancel anything that appears on both sides of the equation. The number of chromium and silver atoms are equal on either side, and the sum of the oxidation states are too. The only difference between a redox reaction taking place in a neutral solution versus an acidic solution is the presence of free hydrogen ions, which are pretty much just protons. A solution with a pH below 7 is considered acidic. Balancing an oxidation-reduction reaction in acidic conditions means we need to account for the hydrogen ions when we balance our oxygen and hydrogen in our half reactions. Aqueous dichromate anions react with aqueous hydrogen peroxide to form the chromium 3 cation and oxygen gas. To start off, let's proceed as if our conditions were neutral. Our first step is to balance all atoms except for hydrogen and oxygen. Next, we have 2 chromium atoms on the left and only a single chromium atom on the right. So we'll add a coefficient of 2 to the chromium on the right. Now for the oxidation states. In our dichromate ion, each oxygen has an oxidation state of -2. Since there are 7 oxygen atoms, we need each of our chromium atoms to have an oxidation state of +6 to create a total net charge of -2 across the entire ion. Each hydrogen in the hydrogen peroxide will have a +1 charge, and each oxygen in the peroxide ion, O2-, will have an oxidation state of -1. This gives us the state of H2O2 molecule we need, 0. The chromium 3 ion's oxidation state is equal to its charge of +3. Atoms in simple diatomic molecules like O2 always have an individual oxidation state of 0 and a total oxidation state of 0. We're still following our steps for neutral conditions. Next, let's find our half reactions. Chromium is undergoing reduction, having its charge decrease from +6 to +3 by gaining electrons. Oxygen is being oxidized. Its charge increases from -1 to 0 by losing electrons. Like before, we account for the change in oxidation states by adding electrons to the left or the right. Chromium needs 6 electrons, 3 for each atom to go from +6 to +3. Each oxygen atom went from -1 to 0, meaning each atom lost a single electron for a total of 2. Here is where we diverge from the neutral steps. Using the aqua and aqueous, we can balance the oxygen atoms. Add the right number of water molecules to the opposite side such that each side has the same number of O's. Our reduction reaction needs 7 water molecules on the right to balance the 7 oxygens and the dichromate ions on the left. Then we will use the protons in the acidic solution to balance the hydrogen atoms. Add the hydrogen atoms to the opposite side so that you have the same number of H's on either side. We need 14 hydrogen ions on the left side of our reduction reaction to balance these 7 water molecules we added. We'll add 2 hydrogen ions to the right side of our oxidation reaction to balance the 2 hydrogen and hydrogen peroxide. Back to our neutral steps. It's time to equalize our reactions with least common multiples. The LCM of 6 and 2 is 6. Multiply the reduction reaction by 1 to get the 6 electrons, and multiply the oxidation reaction by 3 to get the 6 electrons. The 6 electrons cancel on both sides, and the 6 hydrogens on the right offset the 6 hydrogens on the left, leaving 8. What's left is our redox reaction balance in an acidic solution. Now let's balance the same redox reaction from before, but in basic conditions. Proceed as if we were working under acidic conditions until we've added our water molecule and hydrogen ions to balance our oxygen and hydrogen atoms in the reaction. A basic solution won't have those free hydrogen ions. Instead, there are hydroxide ions, OH-, floating around. At this stage, we need to add hydroxide ions to both sides for each hydrogen ion we added. Then combine any hydroxide and hydrogen atoms on the same side into water molecules. Now we'll balance the electrons using the LCM of 6 like we did before. Combine the half reactions and cancel like terms. This leaves us with our redox reaction balance in a basic solution. Feel free to visit us at Chegg for videos and pre-solved problems on this or other topics, or to connect with one of our subject matter experts. Thanks for watching!